Okay, so I think we can start. So after the lot of theories in the first day and in the morning, we thought that it was also good to have a phenomenological perspective and a more observational perspective. And so we invited Gregorio Carullo, who's a member of the LIGO-Virgo collaboration and is involved in the ring-down test of gravity, so with gravitational wave data. And today he's going to present essentially his research on this.
Thanks, Paolo. And thanks also all the organizers for the kind invitation. So this talk will be a bit more practical than the previous ones, and it will have an observational perspective. And so the title of the talk is From Black Hole Spectroscopy, which is we now regularly do, so we observe quasi-normal mode spectra. It's not just a mathematical problem. And so I will recap the observations that we do on these quasi-normal modes. And then I will try to, so there is a jump here, right? Because ring down typically inform us on the light ring structure, on the potential. But what we are really interested about is the horizon, right? So there is a jump from light ring to the horizon. And I will try in the end to discuss possible ways in which this jump might happen, observation, so scenarios where this jump might be relevant observationally, and hopefully sparking a discussion. This doesn't work, I don't know why. Sorry, I think. Yeah, I stopped sharing. Yeah, I'm just trying something. Sorry. It was working before, it doesn't work after Zoom, I don't know why. Okay, now it works. Apologies for that. All right, so first I will recap what we have observed. I'll just give a very brief recap of ring down from black hole coalescences, just to highlight the basic physics. Then I will describe the first observation, so the first day that we actually saw a black hole ringing, and then subsequent what you call catalogs, so collection of observations of ring down. And then I will recap some works we have been doing with many collaborators to draw fundamental physics implications from these observations. And we will see to which extent this is possible, of course. And then I will try to have 10 minutes where we discuss recent claims about no-hair theorem tests. So I will try to answer the question, have we tested the no-hair theorem yet? Or do we need future observations, future detectors? And then finally, in the last, hopefully, 10, 15 minutes, depending on how the discussion goes, I will try to highlight avenues to constrain horizon properties through ring down, at least avenues which have a direct observational implications, which we can discuss in this scenario. Okay, so what have we observed? We have observed this. This is so here is the mass of the objects in solar masses. So we have observed coalescences of compact objects. We don't know if these are black holes, right? We have to test this. But these are surely compact objects. We can say that for sure. So you have two objects, 1 and 2, which merge to form a final remnant one. And there are some very famous guys here. There is the first PNS. There are several neutron star black hole binaries. And you see that, so the blue ones are the ones observed in LIGO and Virgo, blue and orange ones, and the red and yellow ones are neutron stars and black holes observed in X-rays. So if you focus on black holes, it's clear that, these are the red ones, these are all the black holes we observe. It's clear that gravitational wave observations are now, far more, they have far more candidates or events compared to X-rays. So these are 90 compact binary mergers. We're going to observed that is of interest to us, because very little people here care about the astrophysics, so you don't care how these binary forms, where their spins are. What we are interested in is observing binaries which give us ring down signatures, for example, so it can inform us about the quasi-normal mode structure. So we have observed, of these 90 events, 49 were confident enough to test general relativity, because of course we have to set very strict thresholds in order to be sure that these events are good enough to test GR. And 22 of them have confident ring down signatures. So we have not observed ring down in one signal, we are observing down in 22 signals, which is a lot. Yeah. So yeah, I was. Yeah. So I put this box because I'm focusing on the massive branch of this binary. So this is the solar mass. This is the solar mass of the binaries. I'm discarding the low mass ones because for current detectors in the frequency band, the low mass binaries do not give us ring down signatures because they merge at very high frequency where the sensitivity of the detector is low. So essentially, we can observe ring down signatures only for this massive branch, and that explains the box here. So this is roughly the population which will be interested.
I think he was asking about the horizontal axis, which is nothing. No, it's nothing.
No, it's nothing. Sorry. No, it's nothing. It's just different events. So these are all. It's a sequence of events. We just placed one event after the other. It's just because it's nice to visualize. Otherwise, otherwise it's a mess. No. But these are just it's just a sequence of events. No, it's not even time ordinated. It's just different events in some way. Otherwise, this is illegible. So yeah. So how do these coalescence happen? Very briefly, I'm sure all of you know this. So when you have a quasi-circular orbit, you have a quasi-adiabatic regime where the two objects in spiral together, they emit energy and angular momentum, the orbit shrinks. And so, but at a certain point, the orbit shrinks so much that the gravitational attraction doesn't make it possible to sustain stable orbits anymore. So essentially, these objects start to collapse one onto each other. And so the first regime is the in spiral, then there is the merger where the plunge and the merger where they collapse and merge. And at this point, a common horizon form, and this roughly corresponds to the peak of the gravitational wave signal we observe. And after that, immediately after that, a very distorted remnant object is formed. And what this remnant object does is that it relaxes towards equilibrium, towards a stationary state. And in doing so, it emits damped normal mode. So you see that the relaxation phase is driven by this damped exponential decay. This phase is described by a cocktail of perturbation theory for the spectrum and numerical relativity for the amplitude, so how the modes are excited. Because of course this will depend on the configuration of the binary, right? It depends on the ratio of the masses, the spins, etc. So this is to visualize how ring down actually arises in a very simple case. It is spherically symmetric axial perturbations. So what I'm doing here is that I'm throwing a Gaussian packet at a black hole, which is represented by its effective potential. The Gaussian packet interacts with the black hole. Part of the packet will be absorbed and part of it will be reflected away at infinity. So I'm just, the last time, so you see there is absorption and then, so the horizon is at minus infinity. I'm using a tortoise coordinate. So the thing I just wanted to mention is that one way to think of a black hole in this case is a filter. You're throwing whatever you want at the black hole filters it according to its own characteristic frequencies, so to its own resonances in a scattering language, in a scattering amplitude language. This is a scattering problem, it's in quantum mechanics, and this is filtering according to its own resonance states, which are the quasi-normal modes, so the solution of the equations that yesterday were described. And then whatever comes out and we observe at infinity is the filtered signal that is composed of this it has this damped sinusoidal behavior. This should be reflected, by the way, but anyhow. So how does this translate in terms of gravitational wave multiples, which is what we observe in our detectors? So you have H plus and H cross, and these are a superposition of quasi-normal modes. So we have three angular indices, three indices. The first two are angular, L and M, and the third one is the Overton index, so it sorts the quasi-normal modes by decreasing lifetime, essentially. So you have an amplitude factor, an angular factor, and then you have the terms which we really care about, frequencies and damping times. So it's the sinusoidal term and the damped exponential term. The interesting thing here is that this is a countable infinity of numbers. Right, so this can go to arbitrary large values. So in principle, you have a countable infinity of observables, but they are fixed only by just two parameters. I'm talking about the uncharged case. Sorry, Oscar, I will talk about the charged case after in a moment. But for now, let's just focus on the standard astrophysical scenario where the black holes have no charge, so just mass and spin. So you have two numbers fixing an infinite number of observables. This means that if we measure, for example, two frequencies and one damping time, you have three numbers determined by two parameters. So the third one is an independent observation with which you can test general relativity. So this is the very simple, basic idea. In reality, it's far more complicated than this, of course, when you try to measure things. But the basic idea is valid. This is called a no-hair theorem test, although there are people who hate this because, for example, Franz Pretorius likes to call this what we test is the final state conjecture. So what we are testing here is, so first of all, the fact that the remnant black hole is of the family of Kerr-Newman. The second thing is that these solutions are determined only by mass, spin, and charge, so that we have really understood uniqueness theorems and no-hair conjecture in GR. But then, not only that, because no-hair theorems are valid for us in totically flat space-time, in vacuum, the solution is regular, right? But this is real black holes, right? There is no vacuum around it. There will be matter, other black holes and stuff. So what we are testing is that even in real scenarios, of course, the other matter has to be far away for this to be valid, but even in real scenarios where, things which we might not have understood can happen, this is still the case. So that this spectrum is determined actually only by the mass and the spin of the black hole. That's the final state conjecture. So yeah, I already mentioned this. If you were active when there were PN tests with binary pulsars, you would have seen these kind of plots. So the idea is that you measure one quantity and you draw a certain region because there is an error. You draw a certain band. Then you measure the second quantity and you draw another band, and this cross into a region. And then you measure the third quantity, and the third quantity has to cross here. If it doesn't, it means that GR is violated. In this case, it's a GR case, so of course they match. The important and interesting thing is that we expect this to be a universal prediction. What I mean is that even if the theory is not GR, even if the object is not a black hole, we expect that when a remnant forms, it relaxes towards equilibrium by emitting gravitational waves which are dominated by the quasi-normal modes, because these are, the resonance states of the system. So they are the states which dominate the relaxation. Of course, there will be modifications, there will be the dynamics of a scalar field, there will be many things to consider, but the general structure of this emission should at least be valid. And we will consider modifications of this, which of course can accommodate deviations from the standard GR picture. That's it for the theory introduction. Let's dive into observations. This is GW5914, the first time we have ever observed gravitational waves, a binary black hole merge, and the first day that we actually saw a black hole ringing. So I'm sure many of you have seen these plots. This is a measurement of the frequency and the damping time of this black hole. So in black, you have the GR prediction, and in dotted lines. So these are two-dimensional probability distributions. And we are plotting the 90% contours. So in black, you have the, I'm not sure. What do you mean by 2 sigma?
What that was in the paper that is in the papers that I saw, that was the statement.
Okay. Okay.
Yeah,
I'm not.
So in what, what's the likelihood that you found?
So if you compute the Bayes factor,
yes.
The Bayes factor against the noise hypothesis is the log Bayes factor is 90. The log Bayes factor. So this is pretty confident detection. I'm not, well, if you assume all flat priors, that's immediately a likelihood. So I'm comparing the noise hypothesis against the signal hypothesis, and it's 10 to the 30 more likely that this was a signal than it was noise. So yeah, it's pretty confident detection. I'm not sure which number you're referring to. Maybe we can check that together, but yeah. So this is the frequency. So the signal to noise ratio is more or less 8, which is already kind of enough to claim a detection even for a standard gravitational wave. Of course, it depends when you start to analyze the signal, but still. So this is the frequency, the damping time of the fundamental mode. So in black you have the prediction of GR, and dotted lines you have the measurement of this frequency and damping times when you start to analyze the signal So you use the peak of the waveform as reference time, and then you start later and later. Of course, if you start early enough with just one damped sinusoid, you will measure something which is not consistent with GR, because you are still not in the linear perturbation regime. But if you wait long enough, essentially you can describe the system by linear perturbation theory, and so you get a measurement which is consistent with the prediction of GR. So I'm showing on the right a plot which we have in a paper to show one point, which it's important for this analysis. So this is a whitened plot. It means that we have the reconstructed waveform after the analysis, but it's essentially I'm doing this in the frequency domain. And if you do this analysis in the frequency domain, you have these wiggles before. So the ring down, our models of ring down is just something which is 0 up to the peak, because we don't want to know anything about the pre-merger. Because if I look at alternative theories, for example, I don't know how to predict the merger in alternative theory. So I want to exclude anything that comes before the ring down and just focus on or excise the ring down signal, because that I can predict in some alternative cases. And so, but if you want to do this, this should be 0 up to a point and then start to ring. If you do it in the frequency domain, you have these wiggles which screw up your analysis. So that's no longer the case. And so that's why you have to do a time domain approach. There is a lot of technical details here. I'm just skipping them because nobody cares about that analysis, but it's a formalism we have detailed in this paper. Once you have sorted out all the technical details, you can do many things. One easy and nice thing that you can do, for example, is that you can compute an agnostic frequency reconstruction, as I showed you before. So you just, you take the late part of the signal, you measure the frequency, the damping time, and you have a prediction. You have a measurement. Then you predict the spectrum that would come from GR. So all these colored lines are all the quasi-normal modes for varying M. So this is the L equal 2, L equal 3 for varying M. These are the fundamental modes, so N equals 0. And so this is what we call black hole spectroscopy. So this is the spectrum predicted by GR, all these different modes. And you compare the spectrum predicted by the diagnostic measurement that you did. So this is the simplest and I think more powerful and more convincing way of doing black hole spectroscopy. So you have a prediction of the spectrum, and then you just measure agnostically whatever is in your data. So in principle, we would like to do a Fourier transform of the data and just see peaks, right? That doesn't happen, of course, because the signals are too low. But
sorry, Gregory, what is L equal 2 is in this plot is where?
Yeah, sorry. Now I am plotting also the legend. So these are, so this is L equal 2. Is
okay, L2, M2 is on.
Yes, okay. So and then what you can do is, for example, is you can compute the probability that the stuff you measured overlaps with the mode you would expect, which is the fundamental mode, and of course the probability is the highest for the fundamental mode. No, nothing fancy here, but just to give you a basic example of how this analysis works. And I mentioned this. So, oh yeah.
So can you explain a little bit the contour? Can you explain a little bit the contours? Explain the width there.
Yeah. So sorry. So this is just what you measure if you start to analyze the signal 10M after the peak with a single damped sinusoid. So the black line, so it's the 50 and 90% contours. So these black lines are the measurement from the ring down, and all the colored ones are what you would predict from GR by doing a full IMR in spiral merger ring down analysis. So these are smaller because you have used the full signal to predict them, while here you use just the ring down, which of course is much fainter. Yes, so these ones are 90, so the small ones are 90. These ones here is 50 and then 90. Yeah, it's huge. Yes. In fact, we cannot distinguish between, for example, the 3 minus 3 and 3 minus. So you have 45% probability that this was a 2-2, but also 23 and 27 that it was other modes. So of course we are just at the beginnings, and the precision. So the precision is not enough to pinpoint a single mode, which is something important to acknowledge. Yes. Yeah. For one event. Yes. Yeah. Sorry.
Check here, you just for the moment you just identify from the. You have this prediction and you have this measure. What is the check? What do you check here?
Well, I check that the mode I expect to be dominant, which is the light blue one, is actually the one with the highest probability against the agnostic reconstruction using just a damped sinusoid. But it's a very basic test. I'm going to do something more refined later, but just, I wanted to introduce you to the basics of the idea. Yeah.
Maybe one more question.
Yes, sure. I'm happy for
you marginalize over the starting point. What do you do with the?
Yeah. So this one is done late enough so that you know that you are in a linearized regime.
But this is a parameter in your fit. So
yeah.
I'm asking, how do you treat it?
Here is fixed at 10 m after the peak, but in this paper we also discuss a measurement of this parameter, which tells you that you should go at 10, 15 m farther from the peak to have something which is reliable. That's a very important technical point, but yeah.
Sorry, Gregory, one question.
Yes.
So is there a particular reason why the counter-rotating modes are somehow not excluded? It's just because the frequency for L equal 3 is
this
similar.
doesn't tell. So here the amplitudes were free, so they were just parameters of the fit. So we didn't impose any prediction on the amplitudes. So of course, in a standard situation like this, you would expect that you would impose from GR that the amplitudes of the counter-rotating modes will be very small because the spins are not. So those are important only where the spins are large and down, right? But here we are not imposing anything. It's a basic agnostic test, and so these are just consistent because they have the frequency which is closer to it. Yeah. All right. Okay, this is late. I just wanted to mention this. So we have done it on one, then we start to do this systematically. So we have wrote this package, which is what's used by the LIGO-NVIGO collaboration. It's publicly available. The reason I mentioned it here, and I will upload this slide somewhere, is that we have a tutorial, and if you have a student who's interested in this, you are interested in this, you can measure a real black hole vibration frequency in 3 minutes on your, which I think is pretty cool. But yeah. All right, so done for one, done for all. Unfortunately, life is not that easy. There are many technical things to take into account, the detectors, etc. But after a bit of work, we have compiled the first catalog of ring down only observations. So the thing I showed you before, focusing on the ring down for many different signals. So these are all the signals up to 2019. And so here there is a measurement of the mass and the spin for all the different signals using different templates, so different models with different assumptions. So we have a full in-spiral merger ring down analysis, an analysis which uses only the fundamental mode plus the first overtone, or the higher modes predicted by GR. So when I speak about overtones, I mean higher N indices. When I speak about higher modes, I mean L different than 2, essentially, or L or M different than 2. So higher modes is angular harmonics, overtones is just the N indices. There is a lot of technical, a lot of results and details here. I'm skipping this because I want to go to the interesting part. We've also computed probability, so log Bayes, what we call Bayes factors. So Bayes factors are a probability of one hypothesis against the other, and we have computed probabilities that higher modes were present against the possibility that only the fundamental one was there, that overtones were present, and that modifications from GR were present. Significant enough to claim any of these effects in this analysis, so no higher modes, no overtones, and no modification from GR, because these are smaller. That none of this is larger than 2, so there's nothing very confident here.
Sorry, Gregory. Maybe a naive question. So this is a theory agnostic.
Yeah, in some sense, yes.
So of course you're showing us that. You're also testing overtones. Is there a reason why, for instance, you can imagine situations in which your theory has, I don't know, let's say a breaking of isospectrality, so manifests itself in the signal overtone, but just the first one, the degree of freedom. Right. Can you say with respect to this effect?
At this sensitivity, no. At this sensitivity, no.
Yeah, but
you need much higher sensitivity to do something like that. Yeah. In principle, yes, of course. In principle, you fit with n damped sinusoid, you recover very precise measurement of the frequencies and damping times, and then you can see if they match the prediction from GR for the overtone, or if they are somewhere else where your theory would predict breaking of isospectrality. Yes.
Yeah, but I'm asking, how do you? Why are you calling it the first overtone compared to something else?
Sorry. So before I was using an agnostic template. When I impose overtones or higher mode, I use actually predictions from GR. So the frequencies and the damping times are fixed by the mass and so the free parameters in the overtones case is the mass, the spin, which determine the whole spectrum. So I'm imposing that that's an overtone, and I'm searching for that. For the higher modes, we are also imposing that the amplitudes are the ones coming from a quasi-circular merger. So we extract the amplitudes from full numerical relativities, and then we impose those also. So there are many different assumptions in all these models, but these are the best predictions from GR for these kind of models, at least that we had at the time. Yeah. All right, so I said that I was testing modifications from GR. What do I mean by that? I was using...
Sorry, there is a question.
Can you go back to the previous slide? Is it correct that the rotation is typically around 0.7
Yes.
of the maximum? Is there a reason?
Well,
is it the sensitivity of?
No. It's so what you get from NR, so from full numerical relativity, if you have equal mass binary of black holes merging, then there is the final spin of the remnant is going to be 0.7, just because you have a lot of angular momentum. So even if the black holes are non-spinning, you have a lot of angular momentum from the orbital one, which doesn't get radiated away, and so the remnant black hole will spin at very large speeds.
Essentially, angular momentum conservation.
Yeah. That's which is what I said.
Means that in the real world, typically the black holes are not rotating, the ones that merge.
Yeah. So okay. Yeah. So this is the spin of the remnant one. So the one formed after the coalescence. Yeah. So what the correct statement here? So we don't know precisely if the progenitors black holes are rotating or not. So there are a few cases here in the latest release where there is confident detection of a symmetric combination of the spins, which is different than zero. So we have for sure binaries which have spins, but we are not precise enough to measure the single spin. So we can measure these symmetric and anti-symmetric combinations, and there are binaries which are spinning. But yeah, most of them are either non-spinning or the spins are maybe one on and one off. So it's really hard to deviate from this. So you need kind of very large spins to start to deviate significantly from this, because when you have large spins, of course, you are changing also the attraction. So it doesn't mean that all the spin that you had in the binary before is going to be propagated to the black hole, right? Because in PN, the gravitational attraction changes with spins.
Sorry, Gregory, if I can just add something on this to answer to Oscar. It doesn't mean that all black holes in the universe are non-spinning. It means that this family of black holes is most likely non-spinning. For example, if you think about black holes in the supermassive regime, you expect them to be formed with hierarchy mergers, right? And therefore, you will take two of these guys, remnants, which are spinning, and they will form another black hole, and that maybe is spinning even faster. So it probably means that the progenitor here are like first generation black holes. They don't come from previous mergers. Most of them.
Yep. I will discuss this case of near extremal black holes at the end. Yep. All right. So I accelerate a bit. So I meant that I was. So I said I was considering modifications from GR in the previous slide. So here, what would I mean by modifications from GR? In this table, I mean a very simple thing. So I just take the Kerr frequency and damping time, and I modify them one plus delta omega term. So basic parametric deviation, which doesn't have to be small, but and then I measure these across all the events which show some ring down signature, and I combine them together. And this is the result, the latest one that we have published. So you see that the frequency, so this is the probability distribution of the frequency, is consistent with 0 and 90%, and has an error of plus or minus 7%. So this is telling us that combining all the observations we have, we can set the constraint on the fundamental frequency of the of Kerr to be within 7% of what is predicted by GR. And similar cases for damping time, of course, you have a larger error here. And if you calculate a Bayes factor between this modified GR hypothesis, that is this one, and the GR, so where you just this delta omega and delta tau are 0, you get minus 1 log base factor in favor of GR, because this is negative, so it means that the lower hypothesis is preferred. And of course, no, there was a lot of technical work behind this, and we are very happy with this, but at a certain point, who cares, right? So it's interesting that we have prediction, we have a measurement, a constraint on the deviation from care. But what many people are interested about is implications of these observations into specific alternative scenarios, if possible. So now I will try to draw fundamental physics implications. So the point is that it's not immediate. Oh, yeah.
Sorry, just a qualitative question about the movie that you showed at the beginning where there was the scattering process. So this could be also the merging of two black holes and the radiation emitted, represented by this movie with the scattering and some reflected signal that was going back.
I just showed the movie to show how ring down arises in a very simple case. But what you can do is that you can do full numerical simulations of and you see that after when the black holes merge, it's the waveform I showed at the beginning. What happens is that after a certain time, the radiation is well described by a superposition of quasi-normal modes. So although in principle it doesn't have to hold, and it won't hold, for example, in the strong nonlinear regime, after a certain time, your black hole has relaxed well enough that you are in a regime where you can use that.
Okay, so it is a picture also for what is happening in a true black hole merging process.
Yeah, of course, the amplitudes will be, so the ways in which different modes will be excited are different, because it depends on the geometry and how the particle plunges or it goes inward. You understand? Yes.
Yes, but these are just details.
Okay. Yeah, there are details that we can extract from numerical simulations. Yeah. Okay, so it's not easy to draw implications on specific alternatives. You relax the GR assumption, all hell breaks loose. There is isospectrality breaking, there are modes induced by extra fields, and there's many effects that one has to take into account. And also the previous parameterization that I showed, I'm very unhappy with it because it's event dependent. So when we have to combine these signals, we have to use what's called the hierarchical analysis, because that delta omega might change from one signal to the other. It doesn't have any dependence on the spin of the black hole, which is silly, because of course we know that whatever deviation will be, there will be some dependence on how the black hole spins. There is no dependence on extra couplings that might arise in alternative theories. So what I try to do in this paper is that I built on a formalism introduced by the group of Professor Pani, so this paper here, Maselli et al., and I try to take a more informed parameterization of a beyond GR behavior in the spectrum and see what constraints we could draw on that. So the point is that to have a consistent framework to describe these deviations, if you want to apply them to well-motivated classes of modified gravity theories, you have to resort to a perturbative. Perturbatively, you can do it consistently. Simple, you take the spectrum. So this K runs on the quasi-normal mode. So this could be 2 to 0, 2 to 1, etc. So the mass dependence is trivial, of course. And then you can do an expansion in the spin. This is a polynomial expansion, for example. And so you have powers of so you have the linear term in spin, quadratic term, etc. And these will be constants which quantify the dependence on of the spectrum on the spin. Once you've done this expansion, and only then, you start to apply order by order deviations to the spectrum. So now the dependence on the spin is extracted, and so these are already are again numbers. So it's still parametric deviations, but now it's a parametric deviation at each order in spin for each quasi-normal mode. And now this deviation is controlled by this gamma parameter here. And the gamma parameter will be proportional to the couplings appearing in the action. So for example, if your action is introducing some effective length, this gamma parameter will be the effective length normalized by the scale of the system, which is the black hole mass, elevated to some power p. Yes. No, that's fine.
Which kind of coupling exactly you add to the action?
I will.
Ah, okay, thanks.
So I'm just saying, I'm trying to be as generic and simple as possible because I don't want to commit to a specific theory. I want to try to be as generic as possible. So I'm saying, if your theory introduces, for example, a coupling constant, which will have some mass dimension, it will in practice introduce a new length scale. And so this length scale, it's the hell happening here, and the P coefficient will be dependent on the specific theory you are considering. And so the other important thing about this parameterization is that now you are perturbative, so the mass and the spin are the one in GR, because whatever deviation, you can reabsorb them in this expansion. And so if you do all your computation, in the end, it means that you need a much smaller number of signals to detect modifications from GR, because you are imposing more information into your model that predicts some deviations from GR. So the deviation is not, it cannot be whatever it wants. It has a specific structure. And so since you're imposing more information, you can extract more information. But of course, we hope that it's sensible, right? We are doing it in a principled way. So for example, class theories to which this applies. So for P, so as I said, the gamma parameter which will depend by a certain exponent, if the exponent is 0, then the gamma parameter is a scalar coupling. And so for example, you have in this class Lorentz violating gravity, so this Einstein header where you introduce a new time-like vector. So you just have the standard gravity term, and this will be a matrices of many coefficients. Yes. So.
Can you explain do you take into account additional constraints on Lorentz violation coming from other sources?
No.
You just assume Lorentz, but it's excluded at extremely high.
Okay. I'm not assuming anything. I'm measuring this from the data. So I'm measuring this delta omega and this gamma parameter from the data.
No. So if I understand the question, these are Lorentz violation in the gravitational sector, so not in the, say, standard model sector. So they are much less constrained than the standard Lorentz violation. There are still constraints.
So I was asking whether you take something like that into account.
I think the constraints are comparable to what you get. In these theories, you get it from binary pulsars, and they are comparable.
So basically the answer is no.
Yeah.
You don't take that, you look at it.
Right, and then you check whether the bound is competitive or not.
So I think this theory is much more constrained. So the strongest constraint from gravitational waves here comes from the binary neutron star observations, both in electromagnetic waves and gravitational waves. I think that's where the strongest constraints from in this sector. Yeah. No, I know. I'm not. The point is that I'm not assuming this theory, right? I will give all classes of theories. I'll just continue, and maybe this will be clear in a moment. So examples of the classes of theories to which this could be applied are, for P equals 0 will be Lorentz violating gravity. For P equals 2, you have the corrections which would be induced by Kerr-Newman or by a charged dark matter model, for example here. So gravity, standard model photon, you have a dark photon, standard model current, dark current, coupling between the standard model photon and the dark fermions. For P equals 4, you have quadratic. So what I'm saying here is the kind of modifications introduced by quadratic gravity will appear in the formalism before as a P equals 4 P equals 4 exponent in that gamma. And so this is Einstein's Gauss-Bonnet, which will and dynamical Chern-Simons, and I'm sure we will hear more about quadratic gravity in the remainder of the sessions. And for P equals 6, you have a well-motivated class of effective field theories, which is summarized by this effective action. It's by the group of Leonardo Senatore in Stanford. And here you have this is the cutoff. There are 3 cutoffs actually, but this introduces modification which goes P equal to the 6. So now I will be showing. So the point is that I cannot do one analysis and take into account all theories. I have to discretize this P. So I will do one analysis per each P, and then I will show results for each P, and then I will compare also constraints with other observations. So for P equals 0. When you're imposing your analysis that the P is equal to 0, the lowest, so the non-spinning term of the deviations of the frequency, this is the measurement. So you have a bound which is plus or minus 5%, which is not much stricter than what I showed before, but this value was actually obtained before that paper was coming out. So in the end, what you find is that when you use this formalism, you have a reduction of a factor of 4 in the number of events needed to detect a violation. So if we employ all other things being equal, if we impose these parameterizations, we need much less events to start to detect a violation of GR. And so this is the measurement of this coupling. Of course, it depends on how many terms you add in your expansion, so that it will depend on a certain expansion maximum number. But at the lowest order, this is the measurement that you get, which, it kind of hints to be outside zero, but it's still, well within zero at 90%. And the log-based factor is in favor of GR. Then for p equal 4, you have this, so now I'm constraining this effective length coming into the gamma parameter. And so you see that, so now this enters coherently in all the different expansions. So I'm looking at the top one. And so you see the top one at certain 90%, it's around 35. So you can exclude. So this is telling you that if there are new length scales which enter the quasi-Euler mode spectrum of the black hole for p equal 4 coupling, so for quadratic gravity, this length scale has to be smaller than 35 kilometers. Which is, not surprising, because it's the typical length scale of these objects, right? It cannot be anything else. So to compare to other observations, so the best observations we have on this kind of length scales, for dynamical Chern-Simons, combining neutron star and LVC observations, you have something which is order of 30-50 kilometers. And for Einstein scalar Gauss-Bonnet from X-rays, you have something which is 6-10 kilometers. So, this is already competitive to the best bounds we had from other observations. And of course, this can only improve, because I shown 100 events that we have detected. In the next few years, we'll detect hundreds and hundreds, right? And for p equals 6, this is actually the best bound that was published to date. So for effective field theories of beyond GR gravity, which introduced this kind of coupling, the length scale is smaller than 42 kilometers. The previous best known bound was from gravitational wave in spiral, and it was 150 kilometers. But being from the inspiral, it was a long range effect. Now we are probing the finite size effects of the black hole. Just a remark that we can, one of the interesting things about this formula is that if you have, so in many modified gravity, you have predictions only, for example, for the linear in spin term or the quadratic in spin term. You can, if you have only these predictions, you can plug them in. So if you have constraints from if you have theoretical predictions or constraints from other observations, you can plug them in and impose them in your analysis. And whatever terms you cannot compute, you can just marginalize them from the data. So you can just compute them from the data and marginalize them away. So it's a very useful parameterization. I think there's a question there.
So as soon as you're able to study the signal from smaller mass black holes, you can reduce this L very much.
Yes, because so smaller mass black holes, of course, are smaller, so the curvature is larger, so you're probing a length scale which is smaller. So if the detector sensitivity will improve at high frequencies, of course, these bounds will become better. And for example, there is a proposal for a detector called NEMO, which should probe higher frequency. We will strongly improve this, yes.
So these bounds are not the bounds from present observation, but are the bound in case one observe one mode or n modes? No, these are the bounds from present observations.
This is O3N. So it's the first half of the third observing
so in the case, for instance, of Chern-Simon, the shift in the mode is in the axial modes. So you are assuming that what we observed are the axial modes, but aren't the polar modes the most excited in a real coalescence?
The point is that I'm not assuming dynamical Chern-Simons here. I'm assuming a parameterization of the spectrum, and I'm assuming that the length scale is an exponent of p equal 4. One theory which could predict this kind of deviations is dynamical Chern-Simons, and without entering into the specific of the theory, this bound is derived by taking the theory predictions into account. This other bound doesn't. So I'm just comparing the bound I get on the same classes of modifications that would be induced by dynamical.
But it is correct to say that the observed modes are likely mostly polar modes rather than axial.
Well, in that theory,
no, in GR.
Well, but you don't distinguish. So
in a binary, one excites much more the polar than the axial. Is it correct?
So you can what you can say, for example, is how the relative amplitudes of the m+2 and m-2 are excited. So the the polarizations of the modes, but you cannot really say anything directly on the polar or axial kind of modes. I think in this scenario. So that will be encoded in some way in the amplitudes. but yeah, we are not focusing.
So
on that
you don't think that generically in a binary it is most likely excited dipolar? It's not true.
I don't know. I would have to check how this what this implies to the on the amplitude. Okay, so this should have been done in half an hour. It was done in 45 minutes, so I will probably not get to the end of the talk, but it's fine because I like the discussion.
Sorry, another question.
Yep.
Sorry, maybe just I could ask later, but just a comment. So sometimes I would say it might be a little bit too general or not general enough, this parameterization. In the following sense, we would like to input properties, fundamental properties in modified theories of gravity, like locality, Lorentz invariance, and so on.
That effective theory that I showed has all these properties.
Exactly. Yes. So if this so there can be two. It might happen that in some cases this is general enough, so you are you might get stronger constraints if you input this information. On the other hand, some you have shown the EFT of gravity. Some this phenomenological parametrization could not be general enough to capture, right?
Yes, admittedly.
Do you agree?
Yeah, of course. Okay. No, but you know, it's so GR can be modified in infinite ways, right? So the point that if I'm an observer, of course, I'm a trained theoretical physicist and I have my preference towards some scenarios against some others. But as an observer, I have to be as agnostic as possible. I have to try to use parameterizations which accommodate as many reasonable extensions as possible. Of course, if one wants to input specific predictions, one can do so. And I have an example at the end. And of course, if somebody has a specific prediction for the modes which we excited in these mergers, I would be happy to redo the analysis with that specific prediction. But you know, at this level, I think this is the wisest thing to do. Maybe I'm wrong,
but sorry, just following up on your question. Actually, I don't think I agree. This is not general enough. The only assumption here really is that your modification to GR is perturbative. Whatever perturbative correction will be captured by that, maybe with different exponents, but of course if it's not perturbative, it's a different beast, but if it is perturbative, we will capture it.
But we're not including additional modes like the ones induced by, so right. They are included in the sense that, you know, you might observationally mix them for deviations from, so you have two modes and what you observe is a deviation, is a deviation in the first mode, but technically they're not, so for example, the modes induced by the scalar state would not be, they're not immediately taken into account here, although it's very easy, right? You just add the damped sinusoid with a free frequency because you cannot predict the addition, or you impose the frequency of the scalar mode, and so you know it's flexible enough that you can also you know add more input if you need to.
No, I understand that sometimes you like to add the input fundamental.
Yes. Yeah. The point I want to bring is that at least this is much better than was done by LVC, and where LVC is also me, by the way, but this is much better than what we have done in the LVC because it has more physics input. But yeah, I think there's a...
So a lot of discussion. Other question?
Sorry. No. In this case, what do you do? How do you determine the masses and the spin? What do you do for the pre-ring down phase?
I ignore it. I excise only the ring down phase.
And you don't take into account so these you do a general analysis with M, chi, and so on just for the ring down phase, and how do you decide where
in this specific case the mass and the spin are imposed to be close to the GR values because, as I said before, these are the predictions from GR.
Yeah, so you take that from the standard GR analysis.
I don't fix the value. I allow them to be in a range within the 99% credibility. So it's
which you take from the standard analysis with the errors that you get. So it's just GR.
Yeah, because it's motivated by these formulas. Yes. Okay. So the second part. Well, yeah, the last part, at least at this point, is constraints that we can... Paolo, how much time do we have? Sorry. Okay, I can do this in 10 minutes. So another question that we were trying to answer, so in these papers, we always assume that these black holes are uncharged. So they are rotating, but they have no charge. And so we have, at a certain point, we started wondering about this with Nathan Johnson McDaniel, and then we contacted Oscar, Madi, and Jorge and tried to tackle this problem. So this is done in collaboration with them and other people in our standard crew in Pisa, and John Veitch, which is at Glasgow. So, as I said before, we know that Kerr-Newman family should be the ones describing these black holes. The astrophysical charge is expected to be negligible, and there are well understood mechanisms why this should be true. But it should be observationally confirmed, right? We have observations, we have a prediction, so we should confirm it first in principle. And the other thing is that there are fundamental physics scenarios where this is not true. So where these are charged, but the charge is not a standard electric charge which is induced by a gas surrounding the black hole or a plasma surrounding the black hole. One model is mini-charged dark matter, because the reason why these black holes neutralize very fast is that the curvature is so large that it starts to produce essentially pair production. There is a pair production mechanism, and there are other mechanisms. And so these black holes discharge very fast. But this depends on the ratio between the charge and the mass of the electron. In mini-charged dark matter, this does not have to be the case. So you can have models where these do not have to discharge. You can also have charge induced by magnetic monopoles. You can see charge as an effective parameterization for a vector degree of freedom of gravity or a topological induced charge. And there's a lot of end waving here. But it's also, as a principle, it's a valuable test bed for beyond Kerr effects, right? Because we want to test GR, but we don't really have a theory which we know we can prove it's well posed, etc. But this is a theory. So Einstein-Maxwell is a theory which is well posed, and for which we can compute arbitrary values of the charge and the spin prediction. So it's a test bed for what we are doing. So to verify if these black holes are charged, you need a prediction for the spectrum. This is the work done by Oscar and collaborators. There were other attempts in specific regimes. And so a few years ago, they have predicted this. So this is the fundamental frequency as a function of the spin. For different colors are different values of the charge. So they managed to solve this very difficult problem because the equations are not separable. And they have found that the modes connected to spatial dominate the spectrum. But they were all mostly interested into proving the linear stability of Kerr-Newman. So what we did is that we generated a larger number of solutions, so numerical data, which are in black. We created an analytical representation, so just a fit. So now we have a prediction for the spectrum. We can plug in the prediction of the spectrum in what I showed before. It's the same template, but now the frequencies also depend on the charge. And then once you have that, you have a model which we have a model for gravitational waves where the spectrum now depends on the charge, so you can measure the charge. So you plug in the whole machinery, you turn the wheels, and you get nothing. Unfortunately. So what I mean by nothing is that this is the charge, it's normalized between 0 and 1. This is the probability. The prior distribution is light blue, and all the measurements are comparable to the prior. So this is telling you that there is no information in this data. Why is that? The reason is that the charge and the spin of the black hole are strongly correlated, simply because the light ring has the same dependence on the charge and the spin. If you increase the spin, the light ring goes towards the horizon. If you increase the charge, it has a similar effect. So there is a strong spin-charge correlation between the two of them. Sorry, it has an opposite effect. So you can either this is a measurement for one specific event. This gray region is excluded by extremality. The white region is excluded from the measurement. So the measurement is telling you that the spin and the charge of the black hole can only be in this orange region, which is a strong result, right? So we are excluding very large parts of the parameter space in 2 dimensions. But unfortunately, you cannot tell if this is a highly spinning black hole with a small charge or a highly charged black hole with a small spin. So it's just impossible with this measurement to tell. Which is a pity. So the standard question is, okay, but will future upgrades of the detectors be able to constrain this? Sorry, no, there is one other thing which you can do, is that you can say, okay, I cannot measure anything, but I can do some kind of null test. So I can ask, okay, let's assume that the mass and the spin are more or less what's measured by LIGO and Virgo, and let's see what's the maximum amount of charge which breaks this constraint. So it's a null test, but it's still an estimate of the maximum possible charge that this stuff can have. And so the bound you get is 33%. So this cannot be larger than 33% of the maximum. So next question is, can we measure this with improvements of Virgo and LIGO? The answer is only if the charge is very large. So I'm simulating a Kerr-Neumann ring down in detector data. if the charge is 0.1 or 0.3, you don't measure really anything. If the charge is 0.5, you start to measure a peak. So it go only from the ring down, can only measure very large values of the charge. If you want to do better, you need to input information, for example, from the spiral, which is something you can do, and we are hoping to do. So there are predictions for the dipolar emission in the spiral, for example, and we want also to compare to numerical relativity simulations where these binaries now are evolved. So yeah, this was a recap of what I said before, because this should have been half of the talk, but it's fine. So if you have slept for the last hour, what we can say from current observations is deviations in the fundamental mode are smaller than 5–10%. We can bound new length scales to be smaller than 40 kilometers, more or less. We cannot really tell if these black holes are charged or not. We need either more information from theory or better observations. And we cannot even exclude a naive model of area quantization, which should have been discussed later, but it's fine. So I will skip all of this part, but I want to, so since this is a workshop about the horizon, right? Yes, so this is a workshop about the horizon. I want to spend 1 minute, I swear, to try to answer this question. By the way, so there was a question before. Have we tested the Noether theorem yet? My take is no, nor with overtones, nor with higher modes. If you're interested, come and talk to me. I will be happy to discuss this. But this is a workshop about horizon physics. So we would like to draw implications on the structure of the horizon. Can we do that from the ring down? Well, the standard question, as all of you know, is no, because standard ring down emission is dominated by light ring physics. You can see this in the geometric optic limit, or there are many motivations for this. And there is here is a famous nice paper that describes this in the context of wormholes. But if you start to be more open-minded, you start to take into consideration exotic scenarios or mechanisms which are not fully understood, you might start be able to say something about this. So I will list 4 avenues. I will just list them, and we can discuss them if you like. But I will list 4 possible avenues which can, in principle, have observational consequences. So in practice, you have a bubble, which is the theory bubble. I have a bubble, which is the observational bubble. This is the stuff which leaked from your bubble to my bubble. So this is the thing that I can think of that could give me some signatures of horizon in the ring down. If you have other suggestions, please come and talk to me. I will be very happy to listen to them. Okay, so first one, there is a set of papers by the group of Badri Krishnan in AI Hannover, where they uncovered that horizon so in full numerical relativity, you compute the horizon multiples, and you see that these are very well described by quasi-normal modes, which is something which is not trivial. It's not trivial to expect. And so they found correlation between the horizon multiples, so a quasi-local quantity, with the waveform at infinity. And they also saw this for the shear modes and during the spiral. So the idea here is that there could be measurements at infinity, which are indicators of the behavior at the horizon. Clearly, there are gauge invariance problems here, and you need to build a precise map to link these two. But I think this is interesting and deserves further attention. The second thing is, if you have a quantum modification to the horizon, there might be some effects in principle. So one option is to quantize the horizon area. This will impose several it will impose several effects. So there will be either long-range modifications of the ring down, which is more speculative, or echoes and tidal heating. All I want to say is that long-range modifications on the ring down induced by area quantizations can be testable by current detectors. This is what we have shown. So this is the current measurement. It's compatible with 0. The measurement, this is the coupling constant of the area quantization. We show that with these detectors, we will be able to, if there are long-range modifications to the ring down, we will be able to discern them at the sign sensitivity. I mean that the ring down is dominated by the modes induced by the area quantization. So quantizing the area will impose a discrete spectrum on the frequency, and if those frequencies are the ones entering the ring down, then I can tell. I can tell from this observation. Of course, it's not very well motivated, because you don't expect the ring down to be dominated by something which is imposed on the horizon. I agree, but I'm just saying that this is a verifiable model with current detectors. Another option is the membrane paradigm or brainward gravity. There has been recent work by the group of Professor Pani, and there are also constraints by, in this paper, Mishra et al. And the third option, which is less exotic but possibly improbable, is near extremal black holes. Because ring down is in the light ring, we want the horizon. If you go to extremal black holes, the light ring goes to the horizon, right? So in principle, if you have a near extremal black hole, the ring down will be closer, the ring down will probe regions which are closer and closer to the horizon. There are some observations in X-rays which point to near extremal black holes, but in gravitational waves, we have never seen anything like this in a confident way. Of course, with LISA, as Paolo was mentioning, we could be luckier. So the rates is a big question, but I think this is an interesting possibility. And the final one could be spectral instabilities. I was going to discuss this in detail, but I will, of course, skip this. It's the work of Jaramillo et al., if you have heard about this. So my take-home message is that I'm not convinced that spectral instabilities could be a probe of Planck length of our high-frequency effects, because the spectrum is destabilized, but the time domain signal is not, and this is something that, of course, is known from a long time from works of Nellert, and there's a very nice review by Barause, Cardoso, and Pani, which I think clarifies the physics in a lot of physical scenarios. So these quational mode instabilities have been studied a lot in recent literature, but never under physical conditions, I think, at least in recent years. They were done before. So I'm not convinced that at the moment that this could be actually probes into the horizon. And final take-home message. Of course, if you talk about the horizon, what you want to measure is the horizon flux. LISA will be incredible for this. So the current constraints on a parameter which quantifies the horizon flux is, we haven't really measured this, but it could be 1 plus or minus 50, so you don't measure anything. But with LISA, you're going to do 6 orders of magnitude better. So LISA, if you want to start probing the horizon, of course, there will be low curvature observations, but MRIs in LISA is the thing. And that's it. I hope I managed to convince at least some of you that black hole spectroscopy is no longer only a mathematical problem, as the first speaker was saying yesterday. It's also an observational reality. We do it regularly. And the analysis of these signals can help to test our current gravity theory, investigate the nature of these objects, constrain black hole charges, hopefully search for signs in physics, and maybe infer horizon properties. And that's it. Thank you.
So we have time for, maybe 2 questions, then we can also postpone to the discussion session.
So can we distinguish modified gravity or environmental effect?
That's a great question. So in general, one simple answer to that is yes, because if you have a modification to the underlying theory of gravity, that modifications will have to be coherent across different signals, right? So I observe 100 black holes. Of course, the modifications will also couple with the spin of the black hole, right? So for different spins, but the underlying parameter, so if we can predict the kind of deviations in the different signals, we can also predict the dependence on the spin. So it has to be coherent across all the different signals, while environmental effects will be incoherent, right? So they will be in different environments. So in principle, yes, but of course, we need a specific model of modified gravity and a specific model of environmental effects to distinguish this. But let me say that environmental effects are most probably not an issue for LIGO and Virgo observations. So I didn't show them here, but these tests are clean compared to astrophysical systematics. In LISA, we might have some trouble, but in LIGO and Virgo, it would really be a surprise if that happens.
Just a curiosity. In the list of modified gravities theories that you show, you consider the quadratic ones with scalar Gauss-Bonnet and dynamical Chern-Simons, and afterwards the quartic theories. But in principle, in the middle, there are cubic theories that would actually induce order L to the 4th corrections, like the quadratic ones. There is a reason to not consider those?
So you mean the effective field theory had L to the 6 and not L to the 4?
L to the 4, but with cubic theories, not with quadratic and scalars.
Yeah. So there were considered. So in the paper by the group of Professor Senatore, there is a discussion about this. So I can give you the reference. So it's not understood if those will give you if those theories will give stable equation of motions. or stable black holes.
You are from the point of view of effective field theory. I think there is no reason to discard those theories.
No. I
mean, you are agnostic about the UV completion principle.
Okay. Maybe I should recheck that and start to consider that. No, but let me say that those were really examples. The input from those theory was never considered in the analysis. The analysis is completely
No, I understood. Yeah.
Questions? Okay. Maybe the last one.
So just to be sure that I understood right, the one class of things that you do not capture with your perturbative approach would be if there is no horizon, right? Like if you have a compact object instead of a black hole or a perturbation of a GR black hole, then in principle you could have something that will mimic the ring down of a black hole, but it will have a completely different spectrum.
Yes.
Right. Okay.
So sorry.
No, I guess my question was, can you somehow, how does this feature in your analysis? Could you see this somehow or not?
So there is, in this paper, and probably Paolo, okay, there is I can give you the reference, but there is a paper using there is a paper where they use the membrane paradigm, and you can see that for some values, if you pump up the values of the membrane, the parameters of the membrane, you can start to see deviations also in the early ring down. But to come to your question, in LVK, we also do targeted searches or targeted analysis for echoes. So stuff which has exactly the same ring down in GR, and then, echoes, repetitions. There is both an agnostic one, which doesn't assume any, it just assumes coherent power among detectors after the merger. So it doesn't assume any dependence on, there would be no horizon. And there is another targeted one which relies on a specific model of echoes, and none of these searches have found anything significant. So we search them in a different way, that's what I'm saying. But these formalists cannot accommodate the kind of objects you're thinking about.
Can I make a comment?
Yeah.
I mean, the ring down modes the prompt ring down modes are related to the light rings, and many horizonless objects have a light ring. So it's a little slightly modified with respect to the black hole that they are mimicking, but so
it's stuff that you would expect at late times. Yes.
Yeah, it's more so they will fit the yeah. But
right. Good. Okay. So in that case, you just interpret it differently.
Yeah, this connects very well to the topic of these quasi-normal instabilities, right? You can have a spectrum, an underlying quasi-normal spectrum, which is completely different from the black hole, but the time evolution is actually dominated by the undressed fundamental black hole, which is behind the perturbation. And so only at late times the time evolution will actually start to be. Yes.
The very last one.
No, it's just that we are tied in questions that the audience made, so I want to untie it. Could you expand a little bit on this spectral instability that you were mentioning? Yes. Just generically, what is it?
Okay. Well, generically, what is it is that this is a non-self-adjoint operator. So for self-adjoint operators, you know something. You know that if you perturb the potential of the black hole by an epsilon, the spectrum has to be modified by an epsilon, right? Because you can do standard inequalities and bound the and bound this new. So this is the perturbed, and I can bound the spectrum of the perturbed potential, and it has to be an epsilon far away from the black hole. This is not true for a non-self-adjoint operator, and that's what. So this was known since a long time, of course, but Karamillo et al. In this paper, and there have been many follow-up papers, have clarified the structure of this, the mathematical structure behind this. They've clarified it a lot using a pseudospectral method. So what happens is that here I'm taking as an epsilon perturbation of the spherically symmetric axial modes. They are doing it. You have a perturbation of the potential, which is an oscillatory addition. So you have V plus epsilon delta V. Epsilon is 10 to the minus 3. Delta V is some periodic perturbation, and these high frequencies, so k equal 10. So what happens? The red one is the spectrum predicted by standard Schwarzschild, and the blue ones are the ones which are the perturbed modes. So you see that even for a small epsilon, the modes are completely destabilized. And actually they are going towards horizontal lines because that's what you expect also for neutron stars. So it's understood why they do like this. And these lines tells you the region where these unstable modes can be. So small perturbation to the potential, the spectrum is completely different. This was already found by Nöllert in the 90s. The idea was that you know that if you have a compact potential, then you can, they were trying to make this non-self-adjoint operator self-adjoint. And so one way is to cut off at a certain finite length. And so the idea was to use this to have a complete quasi-normal mode basis. But what it showed is that, so you just take Schwarzschild potential and you discretize it in small steps. And of course, you expect that when the steps goes to infinity, so you are recovering the continuum limit and the spectrum will be the same. This is not true. Even if you increase, so these dashed lines are the spectrum of Schwarzschild. Even if you increase the number of steps, the spectrum is completely different from Schwarzschild. It never goes to Schwarzschild. There appear some new modes which could be exchanged for some Schwarzschild mode, but none of them reproduces the fundamental one, for example. So small perturbation of time potential, completely different spectrum, but the time evolution is practically indistinguishable. So this is the time evolution of a Gaussian packet for the smooth case and the 4-step case. So a very rough discretization of the potential. Even in this very rough case, the time evolution is almost indistinguishable at late time. So this is a memory effect. This is a kind of a memory effect which was pointed out in this review. And so the idea is that the quasi-normal modes are exponentially sensitive to long-range behavior because of the boundary conditions. But the time evolution is not. The time evolution is causal. So the time evolution cannot be dependent by arbitrary changes in the potential. And yeah, so that's why I don't think this is relevant.
That's very short. Sorry, probably this is also silly, but for sure short. But does it mean that you have some non-perturbative epsilon dependence on the exact eigenvalues? So can you explain a little bit more mathematically?
Yeah. So
what is going on?
Well, mathematically.
So if I understood correctly, perturbation theory doesn't work.
Sorry?
Perturbation theory doesn't work.
Well, in a sense, this is still perturbation theory. So it's perturbation. So it's a perturbation on perturbation theory. So you take standard perturbation theory on Schwarzschild, and then you add a small perturbation, another small perturbation to the potential. So in some sense, it's still perturbation theory. The point is that how the perturbed potential and the original potential are connected is non-perturbative, if you want, in some sense. But that's just because of the mathematical structure of the operator, which is not self-adjoint. Because we are always used to think about self-adjoint operators in these cases. But maybe, I don't know. I understand this is not a satisfactory explanation, but they do lay out the mathematical formalism behind this in a quite nice way.
No, I would just see some some non-perturbative contribution coming out. Something.
No, but it's still linear theory. You're not.
Essentially, the results of perturbation theories are exponentially sensitive to small corrections in the potential.
Some presence of e to the minus 1 over x. No, I'm saying something stupid. Just understand.
Yeah, but there is an exponential dependence on the result. It's not that the modes are unstable. It's that you find the spectrum, then you slightly perturb the potential, even infinitesimally, and then the results of the spectrum are, extremely sensitive to the small perturbation. But then on the time domain, you don't see anything.
Since we are not mathematicians, e to the minus 1 over x.
Something like that, yeah. There is a dependence as well.
Just to be complete, otherwise,
Right.
We are physicists. So some formula like this, I don't know, just to make to grasp, to understand.
Yeah, but just to say that but we are not going beyond perturbation theory. This is still perturbation theory. That's what I mean.
Okay, all right. Well, I will say let's thank Gregorio again for a nice talk.